did it.
But mine was a bit weird at first. Like I had to like go through all my.
Okay, welcome back everybody. I hope you had a good snow day and at least got some either relaxation or exercise depending on your traveling situation. Last time we had the midterm, and then before that we had the review for the midterm. And now we're basically, this class, we're going to finish off sound waves. About the first maybe half or a third of the class is going to be the last topic on sound waves. And then we're going to move on to waves on the surface of the ocean. And that's nice to do because it's sort of like maybe the most fundamental oceanographic thing that you can look at. So it kind of actually makes the course a bit more oceanographic. And then also, the surface waves on the ocean, which are called surface gravity waves, are different than sound waves in their physics and in the math that you use. But then there's also a lot of similarities, a lot of connections between the same techniques. And so, for example, things like linearization are going to come up, and equation counting in closed systems, and those sort of same ideas. But there will be some new physics with surface gravity waves, and the key difference is that when we talk about sound waves, we talked about sound waves as what's called in the bulk, meaning we didn't consider any boundaries or like reflecting off of solid objects or anything like that. We just said we just have some room and they're just propagating kind of infinitely. Whereas with surface gravity waves, you really can't do that because the fact that there are waves is fundamentally connected to the fact that there's a boundary. The air-water interface is where the waves are, and so you can't really formulate the wave problem without thinking about the boundaries, and that sort of makes some interesting changes to the mathematics. But just by way of review, so we're going to start off finishing off sound waves. So where we basically were at the end of our previous set of discussions was we had boiled down the linearizations of all of the different equations we had: the Euler momentum equation and the mass continuity equation, and then also the adiabatic constraint. And we derived this one equation called the wave equation. And just to be clear here, these almost look exactly the same. So this is d by dt squared. So the second time derivative of the prime pressure field, the perturbation pressure, is equal to a constant. In this case, it's the square of the speed of sound times the second space derivative of the pressure. And this is called the wave equation. And we solved that equation using a traveling wave ansatz. So something like this, where P prime is capital P times sine of kx minus omega t. That's a traveling wave. And when you plug this traveling wave form into the wave equation, you get constraints that basically says that this traveling wave is a proper sound wave. It does have correct sound wave physics, as long as this equation is true, so that the square of the angular frequency is equal to that same constant, cs squared, times the square of the wave number. And this very important formula is called the dispersion relation. And what that formula does is it relates the spatial properties of the wave, like the wave number or wavelength, to the temporal properties, so that the frequency, angular frequency, or period. And it says that sound waves, they can't mix and match spatial variations and temporal variations arbitrarily. That the space variations and the time variations are locked together in this very rigid relationship, omega squared equals cs squared k squared. And what we'll find when we do surface gravity waves is that there will also be a dispersion relation, but it won't be the same formula. Different wave problems, different types of waves, generally any kind of wave will have a dispersion relation, some kind of relationship between the spatial properties and the temporal properties. But what that formula is varies from case to case. And so the surface gravity wave case is going to be quite different. But this one here, the dispersion relation for sound waves is actually quite similar to some other cases. If you study electromagnetic radiation, then the dispersion relation there is very, very similar. And then we talked about the actual concept of wave speed. So we said there's a couple of different types of wave speeds. And the one that we've been focusing on is what's called the phase speed. And the phase speed of a wave is basically how fast the pattern associated with the wave moves. And the example that's probably the easiest to understand is the wave in a stadium. So people are standing up and sitting down, and then the wave pattern goes around, and it's traveling at a certain velocity. And the important thing to recognize is that as this wave moves around the stadium, the actual people that constitute the wave are not moving nearly as much as the wave pattern moves. You might stand up and sit down, you move a little bit, just only in your chair. But the wave pattern is propagating around, and it's propagating a totally different distance and a totally different speed. And so those are different notions. And we looked last time at this traveling wave formula, and we said, how fast does this thing propagate? And we came up with the formula by imagining an observer that kind of runs along with the pattern. We derived this formula that the speed, c of the wave, the phase speed of the wave, is equal to the ratio omega over k. And so this is true for any traveling wave. So whether you are looking at surface gravity waves or electromagnetic waves or gravitational waves or anything, the phase speed is always omega over k. And in this case, though, the thing that happens with sound waves is that the dispersion relation, if you just divide both sides by k squared here, you get omega squared over k squared equals cs squared. So omega over k is just equal to cs. And so this formula, this symbol c, little c, with no decoration, no little s here, that's the general definition of the phase speed of the wave. And our dispersion relation shows that in the case of sound waves, that speed equals the sound speed. So all sound waves, all of their different c values, they all equal cs. So every different type of sound wave, under the same conditions, so under the same pressure and density conditions, they all travel at the same speed, which is 343 meters per second for standard atmospheric conditions. And this property is very special, and it's called the non-dispersive property. So when all the different waves, and when I say different waves, I mean waves of different sizes, so different wavelengths. You might have a sound wave that has a wavelength of 1 meter, so you have a high pressure, and then 1 meter away there's low pressure. Or you could have a sound wave that was 1 centimeter, or much smaller, actually. And no matter how big or small those waves are, they all travel at the same speed. And that's very, very important, we mentioned, for things like music and speech and using sound waves for communication. Because what it means is that the long waves and the short waves, which correspond to different pitches in our ear, they travel at the same speed. So if I'm playing a piece of music at the front on the piano, say, or on any instrument that has multiple notes at the same time, all of those notes will travel to your ears at the same time, and you'll hear it as if it's a chord, say. Whereas if different wavelengths traveled at different speeds, you would hear maybe the low notes first and then the high notes, or vice versa. And so the music or the speech or whatever would kind of get all jumbled and mixed together as the waves went from the piano strings to your ears. But that's not what happens. They all travel at the same speed, and that's because the waves are non-dispersive, which comes from this particular C equals CS formula that we derived. But the other case of dispersive waves, that's when different wavelengths travel at different speeds, and that also happens in wave systems. And we're actually going to see that when we study surface gravity waves. So that's another reason, another motivation for studying surface gravity waves, which we'll sort of get to towards the end of the class, is that it gives an example of how do waves work when they're actually dispersive, when different wavelengths travel at different speeds. Okay, so the first thing we're going to talk about today is what is the physical mechanism of sound waves? So we've derived all this math, basically. We said, here's our equations like Euler's, momentum conservation, F equals ma, and then we've got mass conservation and all that. And we kind of turned the crank and ground the algebra, and then we ended up with these nice formulas, which are consistent with what we know, like sound speed is 343, things like that. But we haven't talked about, sort of at a more physical, qualitative level, why is it that sound waves propagate at all? Like, what's actually physically happening that's causing them to move at this particular speed, or to move at all? And so today we're gonna talk about how we can understand that by looking at how the pressure, density, and velocity perturbations all are aligned with each other in space, and that'll allow us to understand wave propagation. Okay, so I'll just pause there for a second. Does anybody have any questions about the review or anything like that? Okay, so this section is called the physical mechanism of sound waves. So we have mathematically derived many interesting things about sound waves. Such as dispersion relation, wave speed, etc. But why, from a physics perspective, do these waves propagate? At all. To answer this, we will study how the density, rho prime, pressure, p prime, and velocity, u prime, work together in a sound wave. Okay. So, so we can our starting point is the plane, or sorry, the traveling wave form of pressure P prime of x and t equals a capital P sine kx minus omega t, and our three linearized equations. We had du prime dt equals minus 1 over rho naught dp prime dx. We had d rho prime dt equals minus rho naught du prime dx, and we had p prime equals cs squared rho prime. So these three equations here were the linearized equations that we derived, and we ended up sort of substituting these into each other to end up with this overall wave equation. But to analyze this physical mechanism, we're gonna take a step back and go back to the three original equations and say these equations will allow us to find u prime of x and t and rho prime of x and t. So we know from our traveling wave solution to the wave equation, we know that the pressure field is this sinusoidal form, but we haven't actually written down any explicit formulas for the velocity or the density. But because these three equations, they link all the different properties of the waves together, basically starting from one, we can derive all the others. And that's very generally true in any kind of wave theory. Okay, so let's see, which one did I do first? So we're going to find these two other variables, density and velocity. So density is the easiest one. So we'll say one here, finding the density. Rho prime times t. Since p prime equals cs squared rho prime, we have p sine kx minus omega t, that's p prime, equals cs squared rho prime of x and t. And so we just divide both sides here, and so we get rho prime of x and t equals p over cs squared times sine kx. So that part was really easy. So because pressure and density are related, or the perturbations are related through this adiabatic constraint with the sound speed, if we know one, we can just divide through by the sound speed and we find the other one. So what this tells us is that the amplitude of the density fluctuation is equal to the amplitude of the pressure fluctuation, which is capital P, divided by the square of the sound speed. Okay, and we can do something sort of similar now to find the velocity, but because there's derivatives involved, it's slightly more complicated algebraically, but still not too tough. So the second part is finding the velocity u prime of x t. So since partial u prime partial t equals minus 1 over rho naught partial p prime partial x, we have partial u prime partial t equals minus 1 over rho naught times d by dx. And for p prime here, that's our pressure field, we plug in our travel wave. So we plug in capital P times sine kx minus omega t. And now it's not too bad. It's just that there's a derivative of an integral. So we can take this derivative. So the p is a constant, so we can take that outside. And so we get here minus capital P over rho naught times cosine kx minus omega t multiplied by k. And so we take the sine, when we take the x derivative, sine becomes a cosine, and then by the chain rule, this k that's attached to the x comes out, and so we get here negative p k over rho naught cosine of kx minus omega t. But that doesn't quite equal the velocity, that equals the time derivative of the velocity. And so to get the velocity, we have to do one more step and take the integral with respect to time. So we have partial u prime partial t equals minus p k over rho naught cosine kx minus omega t. So integrate with respect to time. And we get here u prime equals minus p k over rho naught. The integral of cosine is sine kx minus omega t. And then when we integrate, we have to divide by this factor that's multiplying by t. So we multiply that by negative 1 over omega is our integral. And so we get our plus sign back, p times k over rho naught omega times sine of kx minus omega t. And we're almost done. We can actually, you could stop here actually, but we'll do one more simplification because this ratio of k over omega, omega over k is the wave speed. And so, so since omega over k equals CS, K over omega equals 1 over CS. And so we can write this as U prime of x and t is equal to P over rho naught CS times sine kx minus omega t. Now I should make sure that I actually have the right answer. Looks good. Okay. So we started from here. We started from our wave solution, traveling wave solution for the pressure, and then based on that, we derived a formula for the density, and we also derived a formula for the velocity. And these were the three key variables in our wave system. And so now we don't just know that there's some kind of traveling wave, we know the speed, we actually know exactly, as a function of space and time, what is the density, what is the pressure, what is the velocity. We have all the information now. And so now that we have all the information, we should be able to sort of physically pick apart exactly what is causing this wave to actually propagate across space. Okay. Okay, so what we're going to do, and this is basically like, this next bit is just going to be, we're going to draw a diagram and then stare at the diagram for a while and try to understand how does this wave propagate based on looking at it. And this is a bit where I'm not going to write down everything I say on the board. So maybe just making a few little notes for yourself or whatever, or you can always refer back to the video later. Okay, so let's plot U prime, P prime, rho prime on the same graph and think about the physics. Okay. So I'm going to draw three curves here. So the first thing I'm going to draw is our pressure field. So our pressure field, again, I'll just erase it as a reminder. P prime of x and t is just capital P sine k plus t. And we can plot these, for example, at time equals 0. Just as an example, it doesn't matter when we plot it. But so our pressure field, and we're going to draw three graphs here, so I'm going to, let's label this one as P prime. So, and it has amplitude capital P. So it's just some sinusoid, and it's going to start becoming interesting once we draw all the other curves on top of it, which are actually also sinusoids. So the next curve I'll draw is the density. And so I'm just going to draw it as a sinusoid with a slightly different amplitude. And so the red curve here, that's the density. And then for the last curve here, I'll draw the velocity. And I guess I should put here, the density height is P over CS squared. And then for the velocity, these are all sinusoids, so kind of the amplitude I'm drawing is a little bit arbitrary here, but the point is we're just going to look at the structure now and then. Okay. So this graph kind of looks a little bit dumb so far because it's just three sinusoids plotted on top of each other. And when I draw these labels here on different units, basically these are not all comparable. So there's three different sets of units here being used. So it's not true to say that the velocity is somehow weaker than the other two because they're all measured in different units. I'm just drawing them with different amplitudes so that you can distinguish between the three curves. But the key idea, just observing the structure, is that all three variables, density, pressure, and velocity, they're all like lined up with each other. So wherever density is high, pressure is also high, velocity is also high, and so forth. And they also have the same sign. So when pressure is a high pressure, you have a high density, and you also have a positive velocity. Okay. So now what I want to ask is if we were just looking at this structure, like let's say you just observed the density, velocity, and the pressure along a certain distance in x. What do we expect to happen in the future? What's going to happen to this pattern? And we know from our previous analysis that this thing is a propagating wave, so it's going to propagate to the right, and it's going to propagate at this particular speed, cs. But we can actually infer that this thing is going to propagate based on our equations. And so I'm just going to quickly just rewrite here on the right-hand side. We had du prime dt equals minus 1 over rho naught dt prime dx, d rho prime dt equals minus rho naught d prime dx, and d prime equals cs squared rho. Okay. So let's look at a particular region of this graph, and I'm going to try to ask, what do we expect to happen in a moment? Like not right now. This is a snapshot at t equals 0, but what's going to happen just in a short while? So one way that makes it easier to see this is instead of graphing the velocity as just a curve, I'm also going to add arrows that show what direction the flow is moving and how fast. And so here we have a positive velocity and it's a high value. So I'm going to draw a big green positive arrow right there, saying that at this point in the gas, the actual parcels are moving to the right. Whereas on this side over here, we had a negative velocity and a high value, the highest value we have. So over here, the flow is moving as fast as it's going to go, and to the left. And then in between, we see that the velocity is decreasing. It starts off positive and strong, then it's positive and weaker, then 0, then weak and negative, and then strong and negative. So if we wanted to draw this in arrows, we would maybe draw something like this. And then over here, we would draw something like that. So we have strong, positive, 0, weak, negative, strong, negative. Okay. So now, I wish I had more colors, but I'm going to look at a region here. Let's consider this little section of the wave. So, could anyone suggest what is going to happen to the mass of this region of air, or equivalent to the density? And what you want to look at here is look at the velocity. So in this system, mass is carried by the velocity. Just like when we derived the continuity equation, we said that the flow is bringing mass into this box or leaving the box. And so the situation is we've got basically on this side of the box. So this is our sort of test region. So can anyone hazard a guess? What do we expect to happen to the mass in this region of the wave? Is it going to maybe go up, go down, stay the same? And then if you say something, I'll ask why do you think that also. And the key thing to think about is the velocity field, because the velocity is what carries the mass. It might be easier if I located these lines a little better. Here we have a stronger velocity, and on this side we have a less strong velocity. And if you want, you can also compare, the key equation is this one here, that the time derivative of the density, so that's how the mass is going to change, is equal to this negative sign times the density itself times the x derivative of the velocity. Anyone have any thoughts? Yeah.
Is it gonna decrease? Like there's gonna be more mass on the left in the thing?
So there is more mass on the left because so the density is this red curve.
Yeah.
And so over here when we have a high value of that red curve, the peak of the sign, that means that your density is the highest right here, and actually everything is the highest. The highest density, highest pressure, and then highest velocity. And so that's true. So right now there's higher density or more mass on the left. And then in the middle, there's kind of no density. This is really the anomaly. It's not the absolute density, but the perturbation density is 0. But what I want to ask is, so when we have a strong velocity here, that's flowing from this middle part into this region, into this box, is that gonna bring mass into the box, or have mass leave that box, or something? So imagine there's a dense region here, there's lots of gas, the gas is very thick, and then we have a flow from that thick region towards where this box is.
I mean, intuitively, wouldn't that bring mass towards the box?
It does, it brings mass towards the box, into the box, with this fairly high velocity.
Yeah.
And then what about on the other side? We've got this weaker velocity there, what's gonna happen with that?
Less mass is going to be flowed through with that.
Yeah, that's right. So this little arrow is also carrying mass out of the box. So the big arrow is bringing a lot of mass in, and the little arrow is bringing a little bit of mass out because the arrow is smaller, so we have less flow happening. So if you're bringing in a decent amount of mass, and then the amount that's leaving is less, what happens to the overall mass in that box?
It decreases.
So you're bringing more in. You're bringing in 10,
right,
and then 5 leaves.
Right.
So how much more or less do you have?
Density increases.
Density goes up, that's right. The density is going up because we have more inflow than we have outflow. So in general, if we just look at this region of the axis, we're bringing mass in, and that's going to increase the density. Another way, so I'll put here, mass flows in, density increases. So we expect this red curve, right now it's at this particular level. This was the sketch at t = 0, but this red curve in this region is going to go up now because we're bringing more mass in, the density is going to increase. And we can also see that from the equation itself. If the equation itself says that the time derivative of density is equal to minus rho naught, that's just the background constant, times du prime dx. So du prime dx here is decreasing. It's going from its peak here down to 0 on this side. So du dx is negative. So that means we have a negative times a positive times a negative. So this whole thing ends up being positive, which says that the time derivative of density is positive, so the mass is going to increase. And I will just note that the peak of this wave, the peak of the density of the wave, right now is just to the left of our region that we're looking at. So what's going to happen is that because we're bringing more mass into this box and less is leaving, this value is going to be raised. And so we're going to locally raise the density there because of just mass conservation. And that basically looks like this peak pattern is moving to the right because we're raising these values, and if we did the analysis here, we're lowering this value, which we didn't do that. But so this value, we're not actually doing this analysis, but this value is going to drop, and this value is going to raise. This is all because of the actual mass flux that's caused by the velocities that are part of this wave. And so we're bringing more mass across this boundary, less mass is leaving. So this red curve is the density, so that means our density is going to rise up because we have mass flowing in, and so our density is going to increase. And so we can already see that just based on looking at the velocity and the density, it looks like this pattern is moving to the right. This peak is decreasing, and just to the right of the peak, it's rising. So it looks like this peak is kind of moving to the right. Okay.
These curves have maximum at the central points, yeah.
Yeah, so like this is meant to be the maximum of all three.
So how, would the change in time not be zero then?
So that is true. And that's a little tiny bit of a subtlety. And that's because you're looking at the exact peak. So if you look just off the peak, what you'll see is that just off the peak, this is rising, and then this is falling down there.
Okay.
So at the peak, it's like, you know how if you have any kind of curve that has a maximum, like right at the peak of it, there's special properties, derivatives are zero and stuff like that.
Yeah.
So right at the moment where we're looking at the peak of the curve, it's instantaneously not changing because it's rising up and then it's falling down, right?
Yeah.
So it just, if you imagine it was like, so we can think about it like with a surface wave. So you have the surface wave. So as the surface wave propagates on the surface of the ocean is rising and falling, right? And if you look right at the moment where that wave is at its maximum, it's actually not changing because it's changing its direction from going up to going down. Right. And so that's what you're, so that is true. You're pointing out correctly that if we're looking at the maximum, du dx would be zero, therefore d rho dt would be zero, that's true. But that's only true exactly at the peak. And then a moment later, the pattern will propagate. So it's very similar to this phenomenon of the peak height of the wave is a moment where it's actually stationary. But if you look a moment later, the pattern will have propagated and it will be coming down. Yeah, that's a good point. That's a bit of a subtlety about this argument. But if you look anywhere, and that's actually the reason why in this analysis I chose somewhere not at the peak. Because if you look right at the peak, it gets confusing. But if you look in between, in the declining phase, you can see that what's happening is that these high values are moving to this side because these lower values are getting elevated.
Yeah.
Okay. Okay. So far, I basically argued that the density wave, which originally had its peak here, is moving to the right because these density values are going to be higher. And that sounds good because we're trying to show that the wave propagates, and we're trying to understand what's the physical mechanism. And what we're understanding is that the physical mechanism of raising the density is that you're putting more gas into the column from one side than is leaving on the other, and that concentrates mass in that column, and it's fundamentally like a flow transport thing. So you have flow coming in at a higher velocity, flow leaving at a lower velocity, and that's what's channeling the mass. Okay. Well, what about the other two fields? Well, so pressure is really easy. So pressure and density, because of the thermodynamic assumptions we made, of basically that it's adiabatic, no heat transport, Isaac law, first law of thermodynamics, all those things we put together, the pressure and the density are just directly proportional to one another. And that's thermodynamics. So when we raise the density at this point, the pressure, which is the black curve, is also going to rise. So we have here pressure rises due to connection with density. So just due to the thermodynamic, in adiabatic processes, density and pressure just lock together. So when one goes up, the other one has to go up. So now we've shown that the density wave is going to rise up, that's the movement of the density peak. And then the pressure wave is going to also rise up there, that's the movement of the pressure peak. And those things are just locked together. Okay. But the last piece that we haven't talked about yet is the velocity. And so if this whole, the wave works together, right? The pressure, the velocity, and the density, they're all trading off back and forth. They're all influencing each other. And it's only through the action of all three together that the wave works. And the same thing is true in electromagnetic waves. So if anybody, has anybody here taken 4500 electricity? Probably not. Or has anyone seen a diagram of like what an electromagnetic wave looks like? There's these like two vectors that are like crossing. Yeah. So how an electromagnetic wave works is that it's called electromagnetic because it's got both electric fields and magnetic fields, and they work together. And how it works is that when you have a changing electric field that induces a magnetic field, and then the magnetic field induces electric field, and they kind of go back and forth like in a circle where one is causing the other, and then that causes the electric field, and they go back and forth like that. And so that's why, and so in electric waves as well, we basically have two different components of the wave, the electric field and the magnetic field, and they work together to cause this propagation. And the same thing is true here. We have density, pressure, and velocity. And if you only had like two of the three, it wouldn't work. The wave just wouldn't propagate. But of course, physics locks them together. You will have all three, because that's how it works. Okay, so the last bit, though, we haven't talked about is the velocity. And how's the velocity going to change? So at time equals 0, the peak of our velocity is right here. That's our strongest value. And then we have weaker velocities, but still positive as we go this way. And then we have the 0 velocity here, and then negative and stronger negative. Okay, so what's going to change the velocity is going to be forces, right? So the velocity is the speed of the particle, and so that speed is going to change depending on the forces acting on it. And then for our first equation here, specifically, the rate of change of velocity is given by minus 1/rho times the pressure gradient. And so basically, we have a pressure gradient force that points from high pressure to low pressure. And then if that pressure force is trying to speed up, or if it exerts a positive force, that's going to try to speed up the parcels, speed up the velocity. And if it's a force in the other direction, it'll try to slow it down. So the pressure, in this case, is the black curve. And so up here we have the highest pressure here, so I'm going to just draw a little h there. That's for high pressure. And then over here we have the big dip. And so this is the low pressure, so we have a negative pressure anomaly here, so this means this is what the lowest pressure is right here. And so generally, what we're having here is we have high pressure to the left side of our test region, and we have low pressure to the right side. And so can anyone tell me what's the direction of the pressure gradient force in this scenario? Thinking about the test region, is the force going to be to the right or to the left or maybe 0 or something in between?
Pressure gradient pushing that way?
The pressure gradient force is going to be pushing to the right because it goes from high to low. Yeah. Sometimes the minus signs and stuff can be confusing, but pressure force always goes from high pressure to low pressure. It wouldn't make sense if it worked the other way, because then if you had like a low density region, a low pressure region, it would want to flow out of there, and it would go like lower and lower and lower to a vacuum. So that wouldn't make any sense. Okay. So because we have high pressure on this side and low pressure on this side, our pressure gradient force, we usually write that as PGF, is pointing to the right, which means that if we think about a little parcel, we have a parcel of gas that's embedded in our wave here. It's moving to, it has a positive velocity, and now there's a positive force acting on that positive velocity. And so what that means is its velocity is going to increase. So we have a positive force drives u prime to higher values. And so the green curve also, which is the velocity curve, because of this pressure force, that's going to rise up as well.
Bless you.
Thank you.
And so by looking at all three variables, the pressure field is driving the velocity to increase. The velocity field is driving the density to increase because it's transferring this mass. Then because of the thermodynamics, when the density increases, the pressure also has to increase. So you have basically pressure drives velocity, velocity drives density, density drives pressure, pressure drives velocity, and so forth. And so these three variables, they all connect in sort of a circular loop of influence that causes this pattern to propagate downstream. And so this is the physical reason. This is what's actually physically happening within the sound wave that's causing this signal to propagate downstream. It's this three-way interplay between pressure, velocity, and density. And there's actually, if we started with pressure, and then we looked at, we started with velocity and density, but you could start anywhere in this cycle and you would still derive a self-consistent type of explanation. And so, it's really, no one of these variables is like more fundamental than the other. They all influence each other kind of equally, but you kind of just have to pick where you want to start your argument. Okay, so so this is definitely like a little bit subtle, and also this is not something that's in a lot of books. This was something that I had to feel like I was understanding the waves at all. I had to understand how this worked, and so I started putting it forward. But in terms of testability, this understanding relationships like this makes for a great explanation question on a final exam. Like if you were given some of these curves, right? Like which way is the pressure gradient force pointing? Which do you expect velocity to increase or decrease or whatever? This is a good sort of conceptual type explanation question because you don't need to do any calculations, but you can understand physically what's happening just based on the ways in which things are changing across space. Okay. So I don't have any questions about that diagram. I realize it might be a little bit subtle, and you might want to look at the explanation again, but any questions? Yes?
So just like the block that we drew in the green,
Yeah.
that's depicting like the parcel in that space, like
that's right. So you think of at every point along this, there's parcel all along, just like along the chain. Every point has a parcel at that point.
Okay. Yeah.
And I just drew this here because there's actually a force. When we're thinking of the pressure gradient force, that force has to act on something, and what it's acting on is the parcel that is at this position. But it's really the same parcel in all three. It's not just that this parcel is just like the velocity parcel or something.
Okay.
Right? It's just whatever parcel's at that position.
Okay. Thank you.
Can anyone see, is the recording still doing okay?
Yep.
Okay.
I've been checking.
Okay. All right, so that's it for sound waves. So the next totally new topic is a new section of the course called surface gravity waves. Better. So these are waves that we normally see. This is along the ocean we're talking about. These everyday waves we've all seen from a boat or on a dock or whatever. So waves on the surface of the ocean are called surface gravity waves. And I'll just make the terminological point that gravity waves are something different from gravitational waves. A gravitational wave is like, you might have heard of like LIGO or gravitational wave detection, and it's like things involving black holes and stuff like that. So a gravitational wave is a wave in the gravitational field, whereas gravity waves are the waves on the surface of the ocean. So two totally different things. So the physics of these waves depends strongly on the water depth. Compared to the wavelength of the waves. So we draw a diagram of a cartoon ocean. So generally, we call the depth of the ocean, we call that capital H, is the usual notation in oceanography. And then this distance here would be lambda, the wavelength of the waves. So two cases. So when lambda over H is much smaller than 1, that means that effectively H, you think of H as very large. It's a very, very deep ocean. That brings this ratio down. And so these are called deep water waves. And this is the case we're going to do. So we will study this case of deep water. And this is corresponds to essentially all wind-driven ocean waves in the open ocean. And in case 2, well, the opposite of deep is shallow. So lambda over H is bigger than 1. These are called shallow water waves. And these are also important. For example, these are tsunamis and waves approaching the shoreline. So like breakers and surf. So what we're going to do over the next couple classes is we're going to do a similar type of approach that we did for sound waves, but with a very different setup. And we're going to study the case of the deep water waves. And this is basically anytime you have like a storm or a hurricane or there's just gentle breeze over the surface of the ocean that generates these waves. And you go out to Cape Spear or anywhere, you can see the waves coming in. Well, so the Cape Spear is a bad example because there you're close to the shore. But so if you're out in the open ocean, then those waves that are originally formed by storms, those are deep water waves because the waves tend to be maybe 5 meters wavelength, maybe less, 10 meters wavelength. But the depth of the ocean, for the open ocean, H is roughly 4,000 meters, or 4 kilometers. So a useful number is, you don't have to memorize this, we'll always put on a formula sheet, but it's useful to know that the average depth of the open ocean, not close to the continental shelves or the shorelines or anything, is about 4,000 meters on average. And so if you have normal surface waves that you would see on the side of a boat or whatever, they're clearly much, much shorter in terms of their wavelength than 4,000 meters. And so essentially all wind-driven waves are deep water waves. But shallow water waves are also very important. So tsunamis are surface gravity waves. They are surface gravity waves, but they're not caused by wind. They're caused by underwater earthquakes mostly, but there's also a few other mechanisms. And the thing about tsunamis is that their size is enormous. They can be hundreds of kilometers across. Their wavelength is hundreds of kilometers. So even though the ocean is 4 kilometers, that's actually shallow compared to a tsunami. So tsunamis behave like shallow water waves, whereas normal wind-driven waves are deep water. Another case where the shallow water waves are very important is if you have a deep water wave, let's say you have some offshore storm, and then those waves propagate away, and at a certain point they hit the beach, right? And so these waves, as you go up to the beach, the depth of the water goes to 0. Right? At the shoreline, the depth is 0. So at some point, your H is going to go to 0, and so waves can become shallow water waves near the beach. And there's a whole very, very nice theory of what happens to waves in shallow water. But it turns out to be kind of similar to sound waves. And so we're going to focus on the case that's a bit more interesting for us, which is deep water waves, which is also just a more generic case of wind-driven waves. What we're going to find, and this is another reason for considering deep water, is that the deep water waves are going to be dispersive. So the different wavelengths travel at different speeds, whereas shallow water waves are non-dispersive. So shallow water waves kind of work like sound waves, that all the different wavelengths travel at the same speed, but deep water waves are different. Okay. So, here's our physical setup. As a simple model of deep water physics, we will consider an ocean that is infinitely deep. So z goes to minus infinity at the bottom. We will have a free surface near z equals 0, defined by z equals eta of x and t. And so this little weird n, that's the Greek letter eta. And that's the typical symbol that we use for free surfaces. And so basically what the setup here is we imagine the surface of the ocean on average is at z equals 0. But when we say there's a free surface, what we mean is that the surface can move up and down. The surface is not at a fixed position. And just like in real ocean waves, the surface bobs up and down, it can move in space and time. And so we have some kind of undulating surface. And the height of that surface, that distance above 0, is going to be called eta of x and t. So eta is the function defining the height of the free surface at x and t. And then we have z goes to negative infinity, and so there is no bottom. So we're just saying the ocean's infinitely deep. And to the extent that we're studying deep water waves, the idea of the different physics here is that if you have a shallow water wave, in shallow water, the waves actually feel the effect of the bottom. So they feel, for example, frictional forces from the bottom. And then also, the fact that there's a hard boundary there means that the wave kind of can't go through the bottom. So it also imposes a geometrical constraint, and then there's also forces like frictional forces. But for deep water waves, the idea is that the ocean's deep enough that the waves basically don't even notice that the bottom is even there. So we can send our bottom all the way down to negative infinity. It's not going to affect the physics because the presence of the bottom already doesn't affect the waves because we're in that deep enough regime. Okay. So next time, we'll start looking at our usual suspects, the Euler equation, mass continuity, etc. So we'll stop there, we're out of time. But next time we'll pick this up and you'll get the tests back. I'm not going to, as with the first midterm, I'm not going to solve the problems. I'm not going to go through the midterm in class. But what I will do is post the solutions with the tests so you can check and use it to prepare for the final exam. Okay, so we'll stop there, and I will see everybody on Tuesday. And you can keep an eye on Brightspace, and the marks will. I'm very hopeful we'll come up with it again.
Thank you.
Yeah.